hypothesis testing in regressions. Yes, because we love hypothesis testing so much, we're going to keep on doing it because, yes, we love it so much. Did I say how much? I mean, and we love it because it's really important. So bear with me. Let's go through some stuff. We do a lot of hypothesis testing on one or several regression coefficients. Now, there's an important distinction between doing a t-test on an individual regression coefficient versus an f-test on a set of regression coefficients taken together. Sometimes all of the slope coefficients overall. In the univariate regression, the t-test on significance gives the same p-value as the f-test for whether all the x variables jointly are different from 0. Because, in a univariate regression, all of them is the same as one of them. But with multivariate regression, the f-test is testing whether all of the slope coefficients are, each and every one of them, 0. Remember, from the univariate case, a 0 slope of the regression says there's no relationship between x and y. Y goes up and down, x goes left and right, but if there's no relationship, then that's a 0 slope. In the multidimensional case, with lots of x variables, the 0 slope generalizes. Often we want to form tests about whether a group of beta coefficients are all equal to 0. It's different than testing if they're one at a time different from 0. For instance, we have a bunch of dummy variables for education. We might want to test whether education overall is useful in prediction. That can be done with the linear hypothesis package in R. Now let's take a step back and think about how these tests are generally set up. We measure the accuracy of the model with the sum of the squared errors. Remember back when we introduced ordinary least squares, explained the procedure was to minimize the squared errors, make the squares least, thus ordinary least squares. Each error is y minus the predicted value, based on the model, squared. The model coefficients are chosen to make those squared errors as small as possible. So an accurate model has a smaller sum of squared errors. If I add one or more x variables, then the error is generally not going to increase. In fact, certainly not going to increase. At worst, the new x variables might be totally useless, but in general, even if they're random numbers, they might improve things a little bit. Which is a bit of a problem, because a rule add x as long as it reduces the sum of squared errors would be no good at all. Instead, I have to ask a more sophisticated question. Did the sum of squared errors go down a lot? Is that a big reduction in the sum of squared errors? This goes back to what McCloskey identified as the classic statistics problem. How big is big? Is there a big difference in the sum of squared errors between two models where one of them has more x variables? Rational decision making has to make a trade-off. Adding x variables makes the error smaller. Dropping x variables makes the error bigger. What's the best choice? Adding a set of variables is often done in cases where I have like a set of dummy variables, such as a set of education dummies. And of course, a final note, which I keep reminding, is statistical significance is not identical to importance. It's quite possible things could be important, even if they're not statistically significant. Or vice versa, they could be statistically significant, but basically unimportant. We have lots of nice math about statistical significance, but we do not have so much about actual importance. That takes some judgment. Looking a bit deeper at the formulas, the sum of squared errors, sometimes called sum of squared residuals, is the sum of each error term squared. Each error term is y minus the beta hat values times x. When we compare two models, we typically assume one is nested within the other. It's a proper subset with fewer x variables. If we're comparing two models, each has different x variables, then that's a little more trickier. The sum of the squared residuals, SSR, for the base model with fewer variables, that's SSR naught. Then the model with more x variables gives SSR 1. Therefore, SSR naught must be larger. Fewer variables means larger errors. So we then find the percent change in the sum of squared errors. That's, in some sense, the benefit of adding more x variables. But note I wrote a squiggly equal sign there, because this is an approximation. To make it better, we'd want something more like an elasticity than just a percent change. Want to take the percent change in the sum of squared residuals and divide that by the percent change in the number of x variables. In this notation, the base model has k x variables. Model 1 has k plus q x variables. So model naught has n minus k minus 1 degrees of freedom. Model 1 has q more variables, and so q fewer degrees of freedom. That means the percent change in degrees of freedom is given there. Divide the percent change in sum of squared errors by the percent change in number of x variables, and that gives us an F statistic. That formula is complicated enough. I'll note it's only exact if we have homoscedastic errors in the presence of heteroscedasticity. That formula gets uglier. So we let the computer do the calculations. But it's useful to keep in mind the basic insight that this complicated formula is just looking at 2% changes. As for the heteroscedasticity, you can worry about that later or never. It's up to you.